Hi everybody, Mr. Record here, and we're going to take a look at a first video that's going to cover this new topic called L'Hopital's rule. It's kind of a different take on how to find limits. It's going to make maybe finding limits a little bit easier than the way it went maybe in the beginning of your year. We're going to talk a little bit about the history of this particular individual, how his name can be spelled different ways, how to pronounce it. It should be pronounced L'Hopital. It is a French word. That O is typically a long O sound, and really how to use it. So let's dive in. So as we can see here, the the idea is obviously to take a limit. And in our particular example here, it says, we'll recall earlier that we did analyze problems like this. And we think, well, how did we solve those? And the notion of plugging in the targeted value of C, which is what I call in my class at Avon High School a green light method. That means that you just simply plug and chug and spit out an answer, but that rarely is allowed to happen, because that poses some big problems for the limits above. So as you can see with those two limits, if we try the green light method, if we try to let x equal 2 in both the top and the bottom, we get 0 divided by 0. If we try to plug infinity into the top and the bottom of this next expression, it results in a negative infinity on top over a positive infinity on bottom. Now, the reason why we get a negative infinity on top is more so due to the fact that this negative sign with this 5x squared sort of takes precedence in this particular question and rules out what 1 minus 4x are really going to do. But in any event, you have these things that I'm now going to give a official name to. I'm going to call these indeterminate forms. It's very important, indeterminate forms. And in calculus AB and BC for that matter, these are the indeterminate forms that we must be concerned with. Now, these other indeterminate forms are things that you could see in future study of calculus. But for now, we're just going to focus on these 5. So that's what the problem looks like that requires L'Hopital's rule. Well, what are we going to do to solve it? Well, basically, the reason why this becomes so important is because we're going to encounter some kinds of problems that we can't do a whole lot of algebra to. In other words, these two limits that you see right here, there's nothing that we could have done in Unit 1 to really solve those very effectively, because we have like a mixture of algebraic pieces with trigonometric pieces, or let's say we have exponential pieces with algebra pieces, and they don't work well together. But as you can see from their graphs, it's very likely that they have answers for their limits. We just have to figure out a way to find them. And so what L'Hopital's rule tells us that we can do on our next page is in the blue box. So you've got a problem that you're trying to take the limit of. I get it. But if you take the limit of the numerator, you get a 0. And if you take the limit of the denominator, you get a 0. Or maybe you take the limit of the numerator and get some kind of an infinity. And the limit of the denominator gives you some kind of infinity. What that means is that you can simply take the limit of the original problem by rewriting it using the derivative of the top and the derivative of the bottom to form your new fraction. And then you let x approach c. Now, keep in mind, this does not suggest that you're using the quotient rule, because that's how we normally take the derivative of f divided by g. This is saying physically take the derivative separately of the top and separately from the bottom, and then plug in your c. Okay? Now, if that works, that's going to be your answer. You're going to get some numerical value, or maybe you get a does not exist, but you're not going to get a 0 over 0 or an infinity over infinity. Oh, well, maybe you could get those, at which point you do L'Hopital's rule again. All right, and we'll see some examples of that. Let's talk a little bit about L'Hopital historically here. L'Hopital was a French mathematician. His full name was Guillaume François Antoine de L'Hopital. and he's credited with the first text on differentiable calculus. And he had actually published this rule in a tome that gave him credit for its discovery, but it was discovered that there were a pair of brothers from Switzerland, the Bernoulli brothers, who actually first came up with this. And so that kind of caused L'Hopital to backpedal and further comment that I acknowledge that I owe very much to the bright minds of the Bernoulli brothers. So he eventually gave credit. There's some rumors, there's some documentation that there was a little exchange of money as well in order for him to not have to completely rescind his findings. In any event, believe what you want to believe. And then I also want to discuss the other issue here. L'Hopital sometimes is spelled two different ways, and it's really not a big deal. Sometimes people make such a big fuss out of it. They're both correct. Historically, L'Hopital with the S was how we initially would see this name, but the French language has evolved a little bit and used more accent symbols where we can drop the S. They're both going to be fine. I know it looks like hospital, but we typically pronounce it L'Hopital. Let's go ahead and take a look at example one where we're going to work through 4 problems here. And I am going to preface this problem 1A with a very important point that I need to make sure is expressed. Before you can really use L'Hopital's rule, you are 100% obligated on an AP free response question to split apart the numerator and the denominator into 2 separate limits. And so the students would physically have to write this on their paper. We could not earn full credit. We cannot give full credit unless we do this. Now, if we plug 2 in, hopefully you can see that you would get 12 minus 14 plus 2, which is indeed going to be a 0, and then 2 minus 2, which is indeed a 0. What that does is it gives you the license to perform L'Hopital's rule, which means you would take the derivative of the top over, take the derivative of the denominator, and this x should not approach infinity there. It should approach 2. And then I can plug the 2 in for x, and in this case I get 5 or 5 over 1. Okay. Now, of course, there's probably another way to do this if we thought about trying to see if this would factor, and that is a possible solution as well. But L'Hopital's rule tends to be a little bit cleaner, and you're typically going to be able to use it in any event that you have an indeterminate form. Now, I'm not going to write this statement for every one of these problems, but I want to make sure that that's very clear to you if you're watching the video. On a free response question, these 2 sentences must be written. On a multiple choice question on the AP exam, your work's not scored, so you wouldn't have to put it on paper. So if we look at example 3, let's go ahead and we're going to assume that L'Hopital's rule applies, but I'm going to go ahead and verify. So if I let x be -3 on top, I get 0. -3 on bottom is square root of 9 minus 5, which is 4 minus square root of 4 minus 2, and that's 0 as well. So if we take the derivative upstairs, that's the easy one, 1. And if we take the derivative in the bottom, we get 1/2 quantity x squared minus 5 raised to the -5, but then we have to multiply by a 2 times x. Okay? Then, when we finish this up, the limit as x approaches -3, the 2's would cancel. I still have an x in the bottom, but I can bring this x squared minus 5 up to the numerator if I so desired, because it has a negative exponent. And I think now we are allowed to plug in. And if we do that, we would get the square root of 9 minus 5, which is the square root of 4, divided by -3. And that does gives us a final answer of -2/3. All right, moving on to part C. This one's going to be a little bit nasty in terms of trying to determine if we do get a 0 on top or bottom. We probably need to push through and verify, because L'Hopital's rule can give you erroneous results if you use it and you're not supposed to use it. So if I real quickly plug in -2 to the top, I would get -8 plus 4 plus 16 minus 12. Now, if you do this arithmetic, you'll see that you get a negative 4 plus 4. You're going to get a 0 in the numerator. Our denominator is going to be negative 8 plus 32 minus 40 plus 16. And so this is going to be also a 0 in the bottom. So we're going to go ahead and apply L'Hopital's rule. Derivative of the top gives us 3x squared plus 2x minus 8. And the derivative of the bottom will give us 3x squared plus 16x plus 20. Now, let's check and see what we get if we plug in negative 2 for the top and the bottom of x. Now, 3 times 4 is 12. 2 times negative 2 is negative 4, minus 8. I have a 0 on top. If I try it in the bottom, I get 12 plus 16. And I forgot an x there. We ought to fix that before we go on. I apologize. There should be a 16x plus 20 there. So try this again. If we plug in a negative 2, this is going to be negative 32 plus 20. And again, that's going to be a 0 over 0. So we just simply use L'Hopital's rule a second time. In this case, the derivatives are going to get easier and easier with each passing step. So I have 6x plus 2 on top, 6x plus 16 on bottom. Again, if I try to plug in negative 2, I end up with something that's not going to be 0 over 0, right? So let's go ahead and answer. And I think we're going to end up with negative 12 plus 2, so that's negative 10. And in the bottom would be negative 16 plus 16, which is, let's do that again, negative 12 plus 16. I don't know where my mind is today, guys. Negative 12 plus 16. I'm going to double check these. Negative 12 plus 2 is negative 10. Negative 12 plus 16 is 4. And of course, we can reduce that to negative 5 over 2. Okay. One more problem. In this case, 5 minus 4 minus 1 is going to be 0. 10 minus 1 minus 9 is going to be 0, of course. So we know L'Hopital's rule is going to apply, and it's probably likely that we're going to have to use multiple iterations of L'Hopital's rule here. Let's go ahead and see what we get. So that's where we land, right? Now, if you kept taking L'Hopital's rule, you could be in trouble. Because I tried to see if I could trick you here. If you were to plug 1 in right now at this moment, you get something that's not indeterminate. You would get a 12 on top and a negative 19 on bottom, and that turns out to be your answer. But it's very important that you realize if we continue to take these derivatives, we're going to get answers wherever we decide to stop that won't match our actual answer that we have. So know when to say when you're using L'Hopital's rule. As soon as you don't have an indeterminate form, you're done. We've got 3 other videos coming up that will explain some more L'Hopital's rule problems, especially the 3rd and 4th video are especially good because they really talk about what the AP style of L'Hopital's rule question would look like. So you definitely want to tune in for those. Anyhow, thanks for joining, and we'll see you next time.